The moon smells like burnt gunpowder. Every Apollo astronaut reported it. The moment they took off their helmets, the dust that had hitchhiked in on their suits filled the cabin with the stench of a fired weapon. Their eyes burned. Their sinuses swelled shut. One astronaut described it as lunar hay fever, and that was after 3 days. NASA is about to send people back, not for 3 days, for months, to a region of the moon where the ground is actively cracking apart, where the dust has never been tested on human tissue, and where the temperature swings 300 degrees every 2 weeks. The moon is not what you think it is. It is the most hostile surface in the inner solar system. And tonight, we are going to walk through every single way it is trying to kill you. If you enjoy our calm nighttime journeys, remember to like and subscribe. We highly encourage our community to discuss the video topics in the comments and react to other comments. It is the most fun when we share our thoughts. Now, let us begin. Tonight, we are going somewhere that looks familiar, but is not. We are going to the moon. Not the moon of lullabies and love songs. Not the moon of binoculars and bedtime stories. The real moon. The one that smells like burnt gunpowder, cracks open from the inside, floats razor-sharp glass above its surface, and dissolves your bones while you sleep. Over the next 2 hours, we are going to walk through every danger that awaits humanity on the lunar surface. We will discover why the dust that coats your boots is a weapon designed by 4 billion years of bombardment. We will learn that the ground beneath your feet is actively tearing itself apart, producing quakes that ring for hours through the dead dry crust. We will follow 2 superpowers racing toward the same patch of frozen darkness at the South Pole. We will descend into underground lava tubes that may be the only places on the moon where human beings can survive long enough to call it home. And we will ask the question that nobody building rockets wants to answer. Can we actually stay? The moon is not what you think it is. It never was. Chapter 1. The lie we all believe. Close your eyes for a moment and imagine standing on the surface of the moon. Picture it. The silence is absolute. Not the quiet of a library or a forest at dawn, a silence that has never been broken. No wind, no birdsong, no distant hum of traffic or murmur of voices. Nothing. The only sound is your own breathing inside your helmet and the faint mechanical whisper of your life support system cycling air across your face. The ground beneath your boots is soft. Fine grey powder, like flour mixed with ash, undisturbed for 1 billion years before your foot pressed into it. The footprint you just made will last longer than any building on Earth. There is no rain to wash it away, no wind to scatter it. It will sit there for 1 million years, 10 million, 100 million, looking exactly the same as it does right now. Above you, the sky is black, not dark blue, not the velvet of a clear night on Earth. Black. The absolute black of nothing, and hanging in that blackness, the Earth. A blue and white marble no bigger than your thumb held at arm's length. Beautiful, fragile, home. Everything about this scene says peaceful. Every visual cue, every sensation, every instinct tells you that you are standing in a place of perfect stillness. A dead world, a quiet world, a safe world. You would be wrong. 12 human beings have walked on the moon. They stayed for a few hours. The longest visit lasted just over 3 days. They drove a buggy. They hit golf balls. They planted flags and took photographs that became some of the most iconic images in human history. And then they came home. And because they came home safely, because the missions were triumphs of engineering and courage, we built a story around the moon. We decided it was conquered. We decided it was understood. We filed it away in the cabinet of things we had already done and turned our attention elsewhere for half a century. But the Apollo astronauts did not stay long enough to learn what the moon actually does to you. They were visitors, passing through too quickly for any of the dangers to fully reveal themselves. And the most immediate danger, The one they noticed first, the one that every single crew reported, and that no amount of engineering could prevent, was the dust. It got everywhere. Not just on their boots and gloves, though it coated those within minutes of stepping outside. It worked its way into the joints of their spacesuits. It scratched their visors so badly that some could barely see through them by the end of a single moonwalk. It clogged mechanical seals and jammed equipment. It ate through layers of spacesuit boots in under 72 hours. It destroyed the vacuum seals on the containers designed to bring lunar samples safely back to Earth. And when the astronauts came back inside their spacecraft, when they repressurized the cabin and removed their helmets, the dust that had hitchhiked in on their suits became airborne. And it stayed airborne. In the 1/6 gravity of the Moon, particles that would settle to the floor in seconds on Earth drifted through the cabin air for hours. Harrison Schmitt was the only trained geologist to walk on the Moon. He was the lunar module pilot on Apollo 17, the last mission to the surface in 1972. Within hours of his first exposure to lunar dust inside the cabin, his eyes began to burn. His sinuses swelled shut. He started sneezing uncontrollably. He described it as lunar hay fever. Other Apollo astronauts reported sore throats, watery eyes, and nasal congestion that lasted for days. And every single one of them noticed the smell. Burnt gunpowder. That is what the Moon smells like when its dust meets oxygen and moisture for the first time in billions of years. What makes this dust uniquely dangerous is not just its abundance, it is what it is made of. The Moon has no atmosphere, no wind, no water. On Earth, rocks are weathered into rounded grains by rivers and rain and wind. On the Moon, the only thing that has shaped the surface for 4 billion years is bombardment. Micrometeorites, tiny fragments of rock and metal traveling at speeds up to 10 kilometers per second, have been slamming into the lunar surface since before life existed on Earth. Each impact shatters the rock, melts fragments into glass, and blasts the debris across the surface, where it is shattered again and again and again. The result is a powder made of sub-micron glass shards with edges so fine they are invisible to the naked eye. Jagged, angular, chemically reactive, and embedded with nanoscale particles of metallic iron locked inside glassy shells. When this dust contacts moisture, it reacts. When it contacts lung tissue, it bonds. And in the reduced gravity of the Moon, particles 50 times smaller than a human hair can penetrate deep into the lower airways and stay there for months. NASA took this seriously. They formed a group called the Lunar Atmosphere Dust Toxicity Assessment Group to study the problem. They established an exposure limit of 0.3 milligrams per cubic meter for astronauts on lunar surface missions lasting up to 6 months. But here is the detail that keeps researchers up at night. That standard was based on dust collected during the Apollo 14 mission, Highland regolith from one specific location on the Moon. The Artemis missions are targeting the lunar South Pole. The permanently shadowed craters there, where temperatures plunge below -200 degrees, where no sunlight has reached in billions of years, contain dust that has never been tested in any biological model. That dust may be mixed with frozen volatiles and sulfur compounds. Nobody knows what it does to human tissue. Nobody has tested it, and we are sending people to stand in it. In 2025, a new study tested actual Apollo 16 lunar dust against human blood cells for the first time and found that the dust triggered measurable immune activation. The researchers noted that allergic sensitization from repeated exposure could not be ruled out for long-duration missions. Another study from the same year, using the most accurate lunar dust simulants ever created, found that while the dust is less chemically toxic than common city pollution on Earth, it still acts as a significant physical irritant, less toxic than feared, perhaps. But the researchers were careful to note that no simulant perfectly replicates the properties of actual lunar regolith. The real dust, the ancient dust, the dust that has been ground and irradiated and electrically charged for 4 billion years on an airless world, remains a question mark. And the dust is not just lying there waiting for you to step in it. On the moon, the ground beneath your feet is electrically alive. When ultraviolet light from the sun strikes the sunlit side of the surface, it knocks electrons free from the soil. The surface becomes positively charged. And the tiniest particles, the submicron glass shards, are repelled upward by electrostatic force. They float. They hover above the surface in a thin, persistent envelope of suspended glass, invisible and silent. On the dark side, the process reverses. Solar wind electrons accumulate on the surface, building a negative charge, and the particles are launched even higher. And at the terminator, the boundary between light and shadow, horizontal electric fields drive the dust sideways. Scientists describe it as a kind of lunar dust storm. Except this storm is invisible. It is silent, and it is made of razor-sharp glass moving through vacuum. The dust coats you, it cuts you, it floats around you, it follows you inside, and it is only the beginning. Because the moon has something far worse than dust waiting beneath the surface. The ground itself is coming apart. Chapter 2. The moon is electrically alive. We have been told our entire lives that the moon is dead. A frozen relic, a lifeless ball of rock that stopped doing anything interesting billions of years ago. That is one of the most persistent lies in popular science. The moon is not dead. It is shrinking. It is cracking. It is quaking. And it is doing all of these things right now in the same region where NASA plans to send astronauts within the next few years. Here is what is happening. The moon has a core. It is small compared to the cores of larger worlds, roughly 350 kilometers across, made of iron and nickel, and that core is cooling. It has been cooling for 4.5 billion years, slowly, steadily, relentlessly. As the core cools, the entire moon contracts, not by much in human terms. Over the last few 100 million years, the moon has lost more than 45 meters of circumference. Think of it like a grape drying into a raisin. As the interior shrinks, the surface wrinkles. But, unlike the flexible skin of a grape, the moon's crust is brittle. It is a single unbroken shell of rock with no tectonic plates to absorb the strain, no subduction zones to relieve the pressure. When the stress builds to a breaking point, the crust cracks. One section of rock is pushed up and over another, forming a steep cliff face that stretches for kilometers across the surface. Scientists call these features lobate scarps, and the Lunar Reconnaissance Orbiter has found thousands of them. As of the most recent surveys, researchers at the Smithsonian Institution have catalogued over 2,600 small ridges on the moon, all formed by the same compressional forces, all geologically young. Some of them may be forming right now. When these faults slip, when one section of crust lurches over another, the moon quakes. And here is where the moon becomes truly alien. On Earth, an earthquake lasts seconds, sometimes a minute. The energy dissipates quickly through the planet's hot, partially molten interior, which absorbs the seismic waves like a damp sponge absorbing sound. The moon has no such cushion. Its interior is cold, dry, and fractured. When a moonquake strikes, the seismic waves bounce and ricochet through the rigid crust with almost nothing to absorb them. The vibrations ring through the rock for hours. The Apollo astronauts deployed seismometers on the surface and recorded this firsthand. They described the moon as ringing like a bell. One of the strongest shallow moonquakes ever recorded by the Apollo Passive Seismic Network was a magnitude 5 event. That does not sound dramatic by Earth standards. A magnitude 5 earthquake might rattle dishes and crack plaster, but on the moon, that same quake shook the crust for an entire afternoon, and it was located in the South Polar region, the same region that NASA has chosen for the Artemis missions. In 2024, a research team led by Thomas Waters of the Smithsonian Institution and Nicholas Schmer of the University of Maryland published findings that connected that powerful shallow moonquake to a cluster of young thrust faults near the lunar South Pole. Their modeling showed that shallow moonquakes capable of producing strong ground shaking are possible from slip events on existing faults or the formation of entirely new thrust faults. They noted that one young fault scarp sits inside an area called the Gerlache Rim 2, which is one of the candidate landing regions for the Artemis missions. The astronauts would be landing disturbingly close to an active fault. Then, in 2025, the same team went further. They published new research showing that the boulder falls and landslides at the Apollo 17 landing site in the Taurus-Littrow Valley were not caused by meteorite impacts, as scientists had assumed for 50 years. They were caused by moonquakes. The Lee-Lincoln Fault, which runs through the valley just 4 miles from where astronauts Gene Cernan and Harrison Schmitt walked in 1972, has been producing magnitude 3 events repeatedly over the last 90 million years. And it may still be active today. Watters and Schmür developed a method to estimate moonquake probability by studying the size and position of displaced boulders and landslides. Their calculation produced a number that sounds reassuringly small at first. The chance of a damaging moonquake occurring on any given day near an active fault is roughly 1 in 20 million. For the Apollo 17 crew, who were on the surface for 3 days, the odds were vanishingly small. They would have had to be spectacularly unlucky. But Artemis is not Apollo. Artemis is not a 3-day visit. NASA plans to establish a sustained human presence on the moon, and when you extend the timeline, the math changes. As Schmür himself explained, if you have a habitat or crewed mission on the moon for a whole decade, that is 3,650 days multiplied by 1 in 20 million, the risk of a hazardous moonquake becomes roughly 1 in 5,500. Those are better odds than being dealt a 4 of a kind in poker. Not a certainty by any means, but not the kind of risk you ignore when you are planning where to put a nuclear reactor or park a landing vehicle that stands 165 feet tall. SpaceX's Starship human landing system is designed to deliver astronauts to the lunar surface for the Artemis program. It is the tallest crewed lander ever designed. And tall structures on loose, unconsolidated regolith are particularly vulnerable to ground acceleration from nearby faults. The moon's surface is not compacted soil. It is billions of years of pulverized debris, loosely packed, micron-sized to boulder-sized, sitting on fractured bedrock. When a moonquake hits, that material can shift, slide, and liquefy in ways that engineers are only beginning to model. As Schmür put it plainly, he would not want to put a nuclear reactor on an active fault. The American Society of Civil Engineers has begun drafting guidelines for lunar structures, borrowing concepts from earthquake-prone cities like Tokyo and San Francisco. Base isolation techniques, flexible foundations, and structural damping systems designed to protect buildings from sustained ground shaking. But there is a critical difference between an earthquake and a moonquake. An earthquake lasts seconds. You brace, it passes, you assess the damage. A moonquake lasts hours. Hours of continuous shaking in an environment where a single cracked seal, a single ruptured pipe, a single misaligned airlock stands between you and the vacuum of space. The moon's loose, unconsolidated surface makes landslides possible from even light seismic shaking. The permanently shadowed craters that contain the water ice humanity needs, the craters that are the entire reason we are going to the South Pole, have steep, unstable walls that could collapse during the next moonquake. And nobody knows when the next moonquake will come. The Apollo seismometers stopped working in 1977. Since then, we have had no active seismic monitoring on the lunar surface. For nearly 50 years, the moon has been shaking in the dark, and nobody has been listening. Schmür is co-leading the development of a new instrument called the Lunar Environment Monitoring Station, which is scheduled to deploy on one of the upcoming Artemis missions. It will finally give scientists real-time data on seismic activity at the South Pole. But until it is there, we are sending people to a world whose ground moves in ways we cannot predict, to a region we know contains active faults, with equipment designed for a planet where earthquakes last seconds, not hours. The ground is cracking, the dust is floating, and there is nothing above you, no atmosphere, no magnetic field, no shield of any kind, to stop what is pouring down from space. The moon sits naked under the full fury of the cosmos, and the next thing that wants to kill you does not come from below, it comes from above. It travels at nearly the speed of light. It passes through walls, through metal, through flesh, through bone, and there is no material humanity has ever built that can reliably stop it. Chapter 3. The radiation you cannot outrun. On Earth, you are shielded by two invisible layers of protection that you have never thought about and cannot see. The first is the atmosphere. 10,000 kilometers of air stacked above your head, dense enough to burn up incoming space rocks and absorb the majority of the radiation that the sun and the wider galaxy fling at this planet every second of every day. The second is the magnetosphere. The Earth's core generates a magnetic field that extends thousands of kilometers into space, deflecting charged particles from the solar wind and channeling them harmlessly toward the poles where they produce the aurora. Together, these two shields make life on Earth's surface possible. Without them, the planet would be as sterile as Mars. The moon has neither, no atmosphere, no magnetic field. The moon lost its global magnetic field billions of years ago as its core cooled and solidified. What remains is a surface completely exposed to the full spectrum of cosmic and solar radiation. Stand on the moon and you are standing in the open, unprotected, absorbing a radiation dose that would set off every alarm in every nuclear facility on Earth. There are two primary threats. The first is galactic cosmic rays. These are not ordinary light or heat. They are the nuclei of atoms, stripped of their electrons, accelerated to nearly the speed of light by the shockwaves of ancient supernovae and other violent events across the galaxy. They have been traveling through space for millions of years, and they are incredibly difficult to stop. A single galactic cosmic ray particle can be an iron nucleus moving at 90% of the speed of light. When it hits a human cell, it does not merely damage the DNA, it shreds it. It punches through the double helix like a bullet through tissue paper, breaking both strands simultaneously in ways that the cell's repair mechanisms struggle to fix. Multiply that by the hundreds of particles passing through your body every second on the lunar surface, and you begin to understand the scale of the problem. Here is the part that makes engineers lose sleep. You cannot simply build a thicker wall to stop galactic cosmic rays. This is one of the hardest unsolved problems in space engineering. When a high-energy cosmic ray particle hits a thick metal wall, it does not stop. It shatters the atoms in the wall. The collision produces a shower of secondary radiation. Neutrons, gamma rays, charged fragments spraying in every direction. In many cases, the secondary radiation is more dangerous than the original particle. This is called the shielding paradox. Adding more armor can make the radiation exposure worse, not better. The heavier the shielding material, the more secondary particles it generates. NASA has studied this problem for decades, and there is still no material solution that can reliably block galactic cosmic rays without creating a cascade of secondary hazards. The second threat is solar particle events. The sun is not a steady lamp. It is a seething nuclear furnace that periodically erupts with enormous bursts of energy. Solar flares and coronal mass ejections can flood the inner solar system with high-energy protons in a matter of hours. On the International Space Station, astronauts are partially protected by Earth's magnetic field. They can retreat to more heavily shielded areas of the station during solar storms. On the Moon, there is no such protection. A major solar particle event could deliver a potentially lethal dose of radiation to an unshielded astronaut in less than a single day. The Apollo missions were extraordinarily lucky. Between Apollo 16 in April of 1972 and Apollo 17 in December of that same year, one of the most intense solar particle events of the modern era occurred. In August of 1972, a massive solar storm erupted from the Sun. It was a class that would have flooded the lunar surface with radiation levels capable of causing acute radiation syndrome. Had that storm occurred a few months earlier or later, had it coincided with a crew on the surface, the consequences could have been catastrophic. The astronauts would have had no shelter. Their spacecraft offered minimal shielding. The storm missed a crewed mission by mere months, and no warning system that currently exists can guarantee advance notice of the most dangerous solar events. Some eruptions from the Sun reach the Moon within minutes. What does sustained radiation exposure do to the human body over time? NASA's own research roadmap lists space radiation as the #1 risk to astronaut health beyond low Earth orbit. The effects are cumulative and they are devastating. Elevated cancer risk, cardiovascular disease, cataracts, as the lenses of the eyes are slowly damaged by particle impacts, central nervous system degradation. Studies on animal models have shown that exposure to the types of radiation found in deep space can impair cognitive function, reduce learning capacity, and alter behavior. And there is one effect that ties radiation directly to another of the Moon's weapons: bone loss. On the Moon, the reduced gravity already weakens your skeleton. Your bones evolved under the full pull of Earth's gravity. In 1/6 gravity, the mechanical signals that tell your body to maintain bone density are dramatically reduced. Astronauts on the International Space Station lose 1 to 2% of bone density per month, primarily in weight-bearing bones. The Moon's gravity slows this process, but does not stop it. And radiation makes it worse. Galactic cosmic rays, particularly heavy ion radiation, like iron nuclei, stimulate the activity of osteoclasts. These are the cells in your body responsible for breaking down bone tissue. Under normal conditions, osteoclasts and osteoblasts, the cells that build bone, exist in balance. Radiation disrupts that balance. It accelerates the breakdown without increasing the rebuilding. Studies have shown that combining simulated space radiation with reduced gravity produces roughly 20% trabecular bone loss in animal models. 20% of the spongy interior structure that gives your bones their strength gone, not because of aging, not because of disease, because of where you are standing. Your body is simultaneously losing bone from reduced gravity and losing bone from radiation bombardment, and the two effects amplify each other. After 6 months on the International Space Station, some astronauts never fully recover their pre-flight bone density, even after years back on Earth. On a multi-month lunar stay, astronauts would face both reduced gravity and direct cosmic ray bombardment, a combination that no human being has ever experienced. We do not know exactly what happens. We have models, simulations, animal studies, but nobody has ever spent 6 months on the surface of the Moon and come back to tell us what it did to their bones, their eyes, their heart, their brain. The radiation on the Moon is invisible. You cannot see it. You cannot feel it. You cannot smell it. There is no alarm that goes off when a galactic cosmic ray passes through your skull. There is no pain when a solar proton shreds a strand of DNA in your bone marrow. The damage accumulates silently, cell by cell, day by day, month by month. And by the time the effects manifest, by the time the cancer develops or the cataract clouds your vision or the cognitive decline becomes noticeable, it is far too late to undo it. Radiation shreds your DNA. Low gravity dissolves your bones, and the two work together, quietly, invisibly, inside your body, every moment you spend on the lunar surface. But the Moon has another weapon, one that attacks not your biology but everything you build, everything you wear, and every seal between you and the vacuum of space. It attacks with temperature. Chapter 4. The temperature that breaks everything. On Earth, The atmosphere is a blanket, not just a source of breathable air, but a thermal buffer that moderates the extremes of heating and cooling. The air holds heat, it distributes warmth, it slows the rate at which things get hot or cold. Even the most extreme temperature swings on Earth, from the hottest desert afternoon to the coldest polar night, occur within a range that materials and machines can handle. On the Moon, there is no blanket. There is no atmosphere to hold heat or slow its escape. The surface of the Moon is in direct contact with the vacuum of space and the raw energy of the Sun. And what that means in practical terms is 300 degrees of punishment. During the lunar day, which lasts roughly 14 Earth days, the surface bakes. Temperatures on the sunlit side climb to approximately 127 degrees Celsius, that is 260 degrees Fahrenheit. Hot enough to boil water at reduced pressure, hot enough to degrade seals, warp metals, and stress every material exposed to it. Then the sun sets, and for the next 14 Earth days, the lunar night descends. With no atmosphere to trap any residual heat, the temperature plunges. The surface drops to approximately -173 degrees Celsius, that is -280 degrees Fahrenheit. Cold enough to shatter certain metals, cold enough to make rubber and plastic as brittle as glass, cold enough to freeze carbon dioxide solid. The swing between these two extremes happens every lunar cycle. Every 29.5 Earth days, every piece of equipment on the surface goes through a complete thermal cycle, from blistering heat to killing cold and back again. And this is not a gentle transition. Without an atmosphere to moderate the change, the shift can be dramatic. Step from shadow into sunlight, and the temperature difference can be hundreds of degrees across a few meters. Engineers call this thermal cycling fatigue. It is one of the most destructive forces in materials science. When a material heats up, it expands. When it cools, it contracts. Repeat this cycle enough times and microscopic cracks form. The cracks grow, seals degrade, joints loosen, welds weaken. Electronics fail as solder connections fatigue and circuit boards flex. On Earth, thermal cycling is a known problem in aerospace and industrial engineering, but the swings are modest by comparison. On the Moon, the amplitude of each cycle is enormous, and the cycling never stops. Every piece of equipment on the lunar surface, every habitat wall, every solar panel, every airlock seal, every communication antenna, is subjected to this relentless expansion and contraction for as long as it sits there. There is no maintenance crew. There is no overnight delivery of replacement parts. If a seal fails at 2 in the morning on the 4th day of lunar night, you fix it with what you have, or you die. And the temperature is not the only thing bombarding you from outside. On Earth, the atmosphere serves as a shield against incoming debris from space. Every day, roughly 100 tons of space material enters Earth's atmosphere. Most of it burns up. Shooting stars are the visible evidence of this constant ablation. On the Moon, there is nothing to stop the incoming material. Sand grain-sized particles of rock and metal strike the lunar surface at speeds up to 10 kilometers per second. That is roughly 36,000 kilometers per hour. At those velocities, a particle the size of a grain of sand carries the energy of a small caliber bullet. Over 4 billion years, this bombardment has ground the lunar surface into the razor-sharp powder we discussed in Chapter 1. But it has not stopped. The bombardment continues today. A permanent surface structure on the Moon would be subjected to this constant sandblasting. Solar panels would be pitted and degraded. Optical surfaces would be scratched and clouded. Thermal blankets would be perforated. Mechanical joints exposed to the environment would accumulate abrasive dust forced into them by micrometeorite impacts. The Apollo astronauts discovered this in 3 days. Imagine what a decade of it would do. And then there is the specific nightmare of the lunar South Pole. The entire reason humanity is returning to the Moon, The entire reason both NASA and China have targeted this particular region is water. Water ice, trapped in permanently shadowed craters near the poles, deposited by comets and preserved by the eternal cold. These craters are among the most valuable real estate in the solar system. They are also among the most hostile environments in the solar system. The rims of these craters sit in near constant sunlight. That is where you would put your solar panels and your habitats. The floors of the craters, where the ice is, sit in permanent shadow. Permanent, as in billions of years of unbroken darkness. The temperatures inside these craters do not just drop to -173 degrees, they plunge far lower. Data from the Diviner Lunar Radiometer on the Lunar Reconnaissance Orbiter has measured temperatures in some permanently shadowed regions as low as 25 to 50 Kelvin. That is -248 to -223 degrees Celsius. These are among the coldest temperatures measured anywhere in the entire solar system. Colder than the surface of Pluto, colder than the dark side of Mercury, colder than nearly any natural environment ever recorded. Any equipment sent into these craters to extract water ice must survive the transition from the sunlit rim, where temperatures exceed 100 degrees Celsius, to the crater floor, where temperatures approach absolute zero. That transition can happen over a distance of meters. The thermal gradient is nearly vertical. No human technology has ever been designed to operate continuously in this thermal regime. Batteries drain rapidly in extreme cold. Lubricants freeze solid. Electronics behave unpredictably. Metal becomes brittle. Seals that are flexible at room temperature become rigid and crack. The permanently shadowed craters are where the treasure is. The water ice, the oxygen, the hydrogen, the rocket fuel that could sustain a permanent lunar presence and serve as a stepping stone to Mars and beyond. But getting to it means sending machines and eventually people into an environment that is actively hostile to every material and mechanism we know how to build. Every surface danger on the moon, the dust, the radiation, the temperature extremes, the micrometeorite bombardment, attacks from the outside. They grind and batter and irradiate everything exposed to them. But the moon has something else, something deeper, something that explains why all of these dangers exist in the first place. The moon was not always like this. It was made this way, made by an act of violence so extreme that it is difficult to comprehend. And to understand why the moon is trying to kill you, you have to understand how it was born. Chapter 5. Born from Violence. 4.5 billion years ago, the solar system was not the orderly place it is today. There were no clean orbits, no stable planets gently circling a well-behaved star. It was a demolition derby. Dozens of protoplanets, half-formed worlds made of rock and metal and ice, hurtled through the inner solar system on crossing orbits, smashing into each other, merging, shattering, merging again. The Earth itself was one of these protoplanets, young, molten, barely formed, and somewhere in the inner solar system, orbiting at a distance not far from where Earth circled the Sun, there was another one. Scientists have given it a name. They call it Theia, after the Greek Titan who was the mother of the moon goddess Selene. Theia was roughly the size of Mars. And one day, moving at a speed that would have made the fastest bullet look stationary, Theia hit the Earth. The collision was not a glancing blow, though it was not perfectly head-on either. Current models suggest an angled impact, violent enough to vaporize the outer layers of both worlds. The energy released was almost beyond calculation. Rock did not just melt, it vaporized. Both Theia and a significant portion of the proto-Earth were converted into superheated gas and liquid rock, sprayed outward into a vast spinning cloud of debris, orbiting where the Earth used to be. Some models suggest this cloud, called a synestia, was a donut-shaped structure of vaporized rock, thousands of kilometers across, glowing white-hot, spinning furiously. And from that cloud, Remarkably quickly, the moon formed. Some recent simulations suggest it may have happened in hours, not months, not years, hours. Material launched into orbit by the impact coalesced under its own gravity, accreting into a sphere while still glowing with the heat of its birth. A 2025 study, published in the journal Science, used iron isotope analysis of lunar samples, terrestrial rocks, and meteorites to reconstruct the likely composition of Theia. The researchers concluded that Theia originated in the inner solar system, possibly even closer to the Sun than Earth. The impactor that created the moon was not some wanderer from the outer reaches, it was a neighbor. It formed from the same disk of gas and dust as the Earth, grew alongside it, and then one day crashed into it with enough force to reshape both worlds forever. The newborn moon was encased in fire. A global ocean of molten rock, hundreds of kilometers deep, covered its entire surface. Scientists call this the lunar magma ocean. As it cooled over millions of years, denser minerals sank toward the interior. Lighter minerals, primarily a type of rock called anorthosite, floated to the surface like scum on a pot of soup. This floating layer solidified into the bright highland crust that we see today when we look up at the moon. The bright areas, the highlands, are the frozen surface of that ancient magma ocean. The dark areas, the Maria, are where later volcanic eruptions flooded low-lying basins with darker basalt lava. Every feature on the moon, from the bright highlands to the dark seas to the powdered surface, traces back to this moment of creation. And everything dangerous about the moon today is a direct inheritance of that violence. The moon is too small to hold an atmosphere. Its gravity is too weak. Any gases released by volcanic activity or delivered by comets simply drifted off into space over the eons. Without an atmosphere, there is nothing to moderate temperature, nothing to block radiation, nothing to burn up incoming meteorites, nothing to erode the razor-sharp dust into harmless rounded grains. The moon's magnetic field died billions of years ago. Its small iron core cooled and solidified too quickly to maintain the dynamo effect that keeps Earth's magnetic field alive. Without a magnetic field, there is nothing to deflect the solar wind or cosmic rays. The surface is fully exposed. The moon has no plate tectonics. Its crust is a single brittle shell. On Earth, tectonic plates move, collide, and subduct, releasing internal heat and recycling the surface. On the moon, there is no such release valve. Internal pressure builds until the crust cracks, producing the thrust faults and moonquakes we discussed in Chapter 2. And the dust, that deadly, electrically charged, razor-edged powder that coats the entire surface, exists precisely because the moon has been sitting in the vacuum of space for 4.5 billion years, with no atmosphere to shield it from micrometeorite bombardment. Every impact that would have been burned up in Earth's atmosphere struck the lunar surface at full speed, shattering rock, melting glass, grinding the surface into a lethal powder 1 grain at a time for longer than complex life has existed on Earth. The moon is not a failed Earth. It is not a smaller, quieter version of our planet that simply ran out of energy. It is a wound, a piece of the most violent collision in Earth's history that was flung into orbit and frozen in the vacuum of space. It has been slowly dying ever since, cooling, shrinking, cracking, losing whatever gases it once outgassed, losing whatever magnetic protection it once briefly had, accumulating damage from every cosmic ray, every solar storm, every grain of space dust that has struck it over 4.5 billion years. The moon we see in the sky tonight is the corpse of a collision, beautiful from a distance, lethal up close, but it is not dead yet, not entirely. And right now, in this decade, 2 superpowers are racing to be the first to set foot on it again. Not for a visit this time, for a claim. The new space race has already begun, and the finish line is a patch of frozen darkness at the bottom of the world. Chapter 6. The New Space Race. On February 27, 2026, NASA Administrator Jared Isaacman stood at a podium at the Kennedy Space Center in Florida and announced that the Artemis program, America's plan to return humans to the moon, was being fundamentally restructured. The first human landing on the lunar surface since 1972 would not happen on Artemis 3 as originally planned. It would happen on Artemis 4. Artemis 3, which was supposed to be the triumphant return, was being redesigned as a systems test in low Earth orbit, a rehearsal, a practice run, not a landing. To understand why, you have to understand the cascade of problems that had brought the most expensive space program in human history to this moment. The Artemis program began taking shape around 2012. Its centerpiece is the Space Launch System, the most powerful rocket ever built, paired with the Orion spacecraft, a deep space capsule designed to carry astronauts to the moon and back. Artemis 1, the first uncrewed test flight, launched in November of 2022. It sent an empty Orion capsule around the moon and back. It was declared a success, but with a caveat. The heat shield, designed to protect the crew during re-entry, did not perform as expected. Chunks of ablative material came off in ways engineers had not predicted. It took more than a year to diagnose the problem. Artemis 2, the first crewed flight, was supposed to launch in 2024. It slipped to September of 2025, then to February of 2026. Then engineers found a hydrogen leak. Then they found a helium pressurization problem in the upper stage. The rocket was rolled back from the launch pad to the vehicle assembly building for repairs. As of this moment, Artemis 2 is targeting an April 2026 launch. It will carry 4 astronauts on a 10-day trip around the moon without landing or entering lunar orbit. Among them will be Victor Glover, who will become the first person of color to travel beyond low Earth orbit, and Christina Koch, who will become the first woman. The delays are not just technical, they are systemic. As Isaacman put it bluntly, launching every 3.5 years is not a recipe for success. When the gap between missions stretches that long, institutional knowledge erodes. Teams that assembled the previous rocket move on to other projects. Procedures that were fresh in everyone's mind become dusty binders on a shelf. The muscle memory atrophies. And the problems compound because each mission introduces new hardware, new configurations, new variables. NASA's Aerospace Safety Advisory Panel issued a report warning that the original Artemis 3 mission plan, which required too many untested technologies and procedures to succeed simultaneously, carried unacceptable risk. The panel recommended restructuring, and Isaacman agreed. The new plan is to standardize the vehicle configuration, increase the launch cadence to roughly every 10 months, and build capability incrementally. Artemis 3 in 2027 will dock with one or both commercial landers from SpaceX and Blue Origin in Earth orbit and test systems. Artemis 4 and 5 in 2028 will attempt the actual landings. Each step will build on the previous one, reducing the number of untested elements on any single flight. It is a more cautious approach. It is also a more realistic one, but it means that the first American boots on the moon since Apollo are now years away, not months. NASA's Office of Inspector General estimates that the agency has spent approximately $93 billion on the Artemis program between 2012 and 2025, and the bill continues to grow. Meanwhile, on the other side of the Pacific, China is moving forward with quiet efficiency. In October of 2025, the China Manned Space Agency confirmed that all primary prototyping of key hardware for its crewed lunar mission has been completed. The Long March 10 rocket, designed to lift 27 tons to lunar transfer orbit. The Mengzhou crew spacecraft, capable of carrying up to 6 astronauts. The Lanyu lunar lander, which will carry 2 astronauts to the surface. The Wangyu lunar extravehicular suit. The Tansuo crewed lunar rover. All of them have passed their preliminary design and testing milestones. The Long March 10 has completed engine static fire tests. the Mengzhou spacecraft has passed its escape system test. The Lanyue lander has completed landing and takeoff verification testing. China is targeting a crewed lunar landing by 2030. The mission architecture mirrors what NASA once planned for its cancelled Constellation program. 2 separate rockets launch from the Wenchang Space Launch Center on Hainan Island. One carries the Lanyue lander, the other carries the Mengzhou spacecraft with the crew. They rendezvous and dock in lunar orbit. 2 astronauts transfer to the lander, descend to the surface, conduct their mission, and return to the orbiting spacecraft for the trip home. It is elegant, it is methodical, and it is on schedule. China is not stopping at a single landing. The International Lunar Research Station, a partnership between China and Russia with over 50 countries invited to participate, aims to establish a permanently inhabited base on the Moon by the mid-2030s. The roadmap includes robotic precursor missions. Chang'e 7, launching in 2026, will be the first lander and rover to search for water ice at the South Pole. Chang'e 8, planned for 2028, will test technology for manufacturing building materials from lunar soil, in situ resource utilization, the ability to use what the Moon provides rather than hauling everything from Earth. And when the International Space Station retires in 2030, China will be the only nation with a permanent crewed outpost in Earth orbit. Their Tiangong space station will continue operating. Every other nation that wants access to a space station will need to negotiate with Beijing or build their own. The gap between the American and Chinese programs is narrowing. As of this spring, the United States holds a marginal calendar lead, but every Artemis delay shrinks that lead. Both nations are targeting the same destination, the lunar South Pole. Both want the water ice. Both need the permanently sunlit ridges for solar power. Both understand that whoever establishes a sustained presence first will have an enormous strategic advantage, not just in science. In resources, in legal precedent, in the geopolitical architecture of the 21st century, this is not Apollo. Apollo was a visit, a flag and footprints and a handful of rocks carried home in triumph. What is happening now is something different. Both superpowers are positioning themselves to claim territory, extract resources, and build infrastructure on another world. And both of them are aiming for the same small patch of the most hostile real estate in the solar system. But what exactly is waiting for them there? In the craters where sunlight has never reached, and temperatures drop below anything measured on Earth, what is hiding in the dark? And why is it worth risking everything to get it? Chapter 7. Dark Ice. There are places on the Moon where the sun has never shone, not in 1 billion years, not in 2 billion, not since the craters themselves were gouged into the surface by ancient impacts. They are called permanently shadowed regions, and they exist because the Moon's axis of rotation is nearly perpendicular to the plane of the solar system. The Moon barely tilts, while Earth's 23.5-degree axial tilt gives us seasons. The Moon's tilt is only about 1.5 degrees. This means that at the poles, the sun never rises high above the horizon. And in the deepest craters near the poles, the rims are tall enough to block the sun entirely. The floors of these craters have not seen a single photon of sunlight in billions of years. 324 permanently shadowed regions have been identified on the Moon. Their combined area is roughly 31,000 square kilometers, about the size of Belgium, and within that eternal darkness, the temperatures are staggering. As we discussed in the previous chapter, some of these regions reach as low as 25 to 50 Kelvin. They are among the coldest places in the entire solar system. And in that cold, something has been accumulating for billions of years. In 2009, NASA conducted one of the most dramatic experiments in the history of lunar science. The LCROSS mission, which stands for Lunar Crater Observation and Sensing Satellite, deliberately crashed a spent rocket stage into a permanently shadowed crater called Cabeus near the Moon's south pole. The impact sent a plume of debris roughly 10 kilometers into the vacuum above the crater floor. A trailing spacecraft flew through the plume, analyzing its composition before crashing into the surface itself. What they found changed everything. The debris contained water ice, roughly 5.7% by mass, not a trace, not a hint, a significant concentration. But that was not all. The plume also contained methane, ammonia, carbon dioxide, carbon monoxide, hydrogen sulfide, and traces of silver, gold, and mercury. The permanently shadowed craters are not just cold. They are chemically exotic. They are time capsules, preserving volatiles delivered by comets and the solar wind across the entire history of the solar system. The water is why we are going back. Water on the Moon is not just water, it is oxygen and hydrogen. Split water molecules through electrolysis, and you get breathable air and rocket fuel. A permanent lunar base without local water would require every drop of drinking water, every breath of air, and every kilogram of rocket propellant to be launched from Earth at a cost of roughly $1 million per kilogram to the lunar surface. With water, the equation changes. A base near the South Pole craters could produce its own air, its own drinking water, and its own fuel for missions deeper into the solar system. The Moon stops being a dead-end destination and becomes a gas station, a gateway, a stepping stone to Mars and beyond. But extracting that water is a problem that nobody has yet solved. The ice is not sitting in neat blocks waiting to be harvested. It is mixed with the regolith, distributed in varying concentrations through the soil, possibly as thin films coating individual grains, possibly as discrete chunks buried under layers of dust. Nobody knows what form it takes. In 2025, China's fast bistatic radar system, used in conjunction with a lunar orbiter, placed upper limits on water ice content at 0 to 6% by weight in South Polar permanently shadowed regions. That is consistent with what LCROSS found, but confirms that the ice is patchy, not a thick, solid deposit. You cannot simply drive a bulldozer into a crater and scoop up blocks of ice. You would have to process enormous volumes of regolith to extract usable quantities of water, and the environment where you would have to do this is among the most hostile in the solar system. The mercury concentrations found by LCROSS could be a health hazard for astronauts processing the soil. In 2024, researchers demonstrated that water ice in permanently shadowed craters actively weathers the lunar regolith through freeze-thaw cycles, cracking particles and generating additional fine dust. The dust in permanently shadowed regions, dust that has been sitting in near absolute zero temperatures for billions of years, may be even more dangerous than what Apollo encountered. It has never been exposed to heat, never been baked by solar radiation, never undergone the chemical weathering processes that modify dust on the sunlit surface. It is pristine, and pristine in this context does not mean safe. It means unknown. Reaching the ice has already proven difficult. In February of 2025, Intuitive Machines launched its IM-2 mission, carrying a Nova C lander to Mons Mouton near the South Pole. Aboard was NASA's Prime 1 experiment, designed to drill into the lunar surface and search for ice. The lander tipped over after its altimeter failed during the final descent. The same failure mode that had toppled its predecessor, IM-1, the year before, the ice drilling experiment was compromised. 2 attempts, 2 tipped landers. The south pole of the Moon does not yield its secrets easily. The craters are simultaneously the most valuable and the most dangerous real estate in the solar system. The water is there. It is laced with mercury. It is surrounded by dust that has never seen sunlight. The craters sit on active fault lines. Their walls are steep and potentially unstable. The temperatures inside would kill an unprotected human in seconds and destroy most equipment in minutes. And yet, we need what is down there. Everything about a permanent lunar presence depends on it. If we can extract the water, the Moon becomes a base camp for the solar system. If we cannot, it remains what it has always been: a beautiful, hostile, and fundamentally uninhabitable world that we can visit but never call home. The water waits in the dark. The question is what it does to the people and machines we send down to get it. Because the moon does not just attack your equipment, it does not just threaten your habitat and your machinery. It goes after something far more personal. It goes after your body, every system in it, every bone, every muscle, every organ, and it starts the moment you arrive. Chapter 8: What the Moon Does to Your Body. Everything we have discussed so far has been about the external threats. The dust that shreds your lungs, the radiation that breaks your DNA, the temperature that cracks your equipment, the ground that shakes beneath your feet. But the moon has a quieter weapon, one that does not come from outside, one that works from within. Your own body, the body that evolved over millions of years under the specific conditions of Earth, begins to dismantle itself the moment you step onto the lunar surface. Start with your skeleton. Your bones are not static structures. They are living tissue, constantly being broken down and rebuilt by two competing types of cells. Osteoclasts tear old bone apart. Osteoblasts build new bone in its place. On Earth, under the full pull of gravity, these two processes exist in balance. The mechanical stress of standing, walking, running, and carrying your own weight sends signals through your bones that say, keep building. The osteoblasts stay busy. The skeleton stays strong. Remove that signal and the balance collapses. On the International Space Station, where astronauts float in microgravity, they lose 1 to 2% of bone density per month, primarily in the weight-bearing bones, the hips, the spine, the legs. The bones that do the most work under gravity are the first to go when gravity disappears. The moon has 1/6 of Earth's gravity. That is not zero. It is enough to slow the process, but it is not enough to stop it. Your bones will still lose density on the moon, slowly, steadily, month by month. And as we discussed in Chapter 3, galactic cosmic ray radiation accelerates the process by stimulating osteoclast activity. Your body does not just stop building bone. It actively accelerates the dismantling. Studies combining simulated space radiation with reduced gravity in animal models have shown roughly 20% loss of trabecular bone. That is the spongy internal lattice that gives your bones their shock-absorbing strength, 20%. And here is the part that should keep mission planners awake at night. After 6 months on the International Space Station, some astronauts never fully recover their pre-flight bone density, even after years back on Earth. The damage can be permanent. The moon offers no rehabilitation facility. There is no swimming pool for low-impact exercise. There is no physical therapist. There is a treadmill, if you are lucky, bolted to the floor of a habitat the size of a shipping container. And every kilogram of exercise equipment competes with food, water, air, spare parts, and scientific instruments for space on the cargo manifest. Your muscles are next. In reduced gravity, the muscles that work hardest on Earth, the ones in your legs, your back, your core, the ones responsible for holding you upright and moving you through the world, begin to atrophy. Without the constant demand of supporting your full body weight, muscle fibers shrink. Slow twitch endurance fibers, the ones you need for sustained physical labor, are replaced by fast twitch fibers suited for short bursts, but inadequate for the heavy demanding work that lunar surface operations require. Astronauts on the International Space Station can lose 10 to 20% of muscle mass on short missions and up to 50% on long-duration flights without aggressive countermeasures. The countermeasure is exercise. 2 or more hours every single day, running on a treadmill strapped to the floor with bungee cords, pedaling a stationary bicycle, pulling against resistance machines. It is tedious. It is time-consuming. It competes with every other task the crew needs to perform, and it only slows the decline. It does not stop it. Then there are your eyes. Spaceflight-associated neuroocular syndrome is one of the most troubling discoveries of the long-duration spaceflight era. More than half of astronauts who spend extended periods on the International Space Station experience changes in their vision. The leading theory is that redistribution of bodily fluids in reduced gravity increases pressure inside the skull, which in turn presses on the optic nerve and deforms the structure of the eye itself. The optic disc swells. The retina can develop folds. Vision blurs. Some astronauts have needed corrective lenses after returning to Earth that they did not need before their mission. The Moon's 1/6 gravity may produce a milder version of this syndrome than the microgravity of the space station. But milder, on a mission lasting months, is still a crew member whose vision is degrading while they are performing precision tasks in an environment where a mistake can be fatal. Your heart changes shape. In reduced gravity, the cardiovascular system no longer has to pump blood upward against the full force of Earth's gravity. The heart muscle remodels over time, becoming more spherical, less efficient. Blood volume redistributes toward the head and upper body. Astronauts often report feeling congested, as if they have a permanent head cold. The long-term cardiovascular effects of months in lunar gravity are unknown, because no one has ever experienced them. And then there is your immune system. This may be the most dangerous change of all. Research has consistently shown that spaceflight suppresses immune function. T cells, the white blood cells responsible for identifying and destroying infections, become less effective at reproducing and responding to threats. Meanwhile, latent viruses that your immune system normally keeps dormant begin to reactivate. Herpes simplex, varicella zoster, the virus that causes chickenpox and shingles, Epstein-Barr virus. They wake up. In the confined environment of a lunar habitat, where you share recycled air with a handful of other people, where there is no hospital, no pharmacy beyond what you brought with you, and a 1.3-second communication delay to Earth, a compromised immune system is not just a medical concern. It is a mission-critical risk. A simple infection that would be an inconvenience on Earth could become a crew emergency on the Moon. Put it all together. Your bones are dissolving. Your muscles are wasting. Your eyes are changing shape. Your heart is remodeling. Your immune system is standing down. And all of this is happening simultaneously, continuously, from the moment you arrive. The Moon does not attack one system at a time. It attacks all of them at once, silently, invisibly. While you sleep, while you work, while you eat your vacuum-sealed meals and stare out the porthole at the small blue marble hanging in the black sky. But there is one organ the Moon attacks that nobody talks about enough. Not your bones, not your muscles, not your eyes, your mind. And what it does to you there may be the hardest challenge of all. Chapter 9. The loneliest place in the universe. Imagine waking up and not knowing if it is day or night. Not because you forgot to check the clock, because the concept has lost its meaning. On Earth, your body runs on a 24-hour internal clock called the circadian rhythm. It governs when you sleep, when you wake, when your hormones rise and fall, when your body temperature peaks and dips, when your mind is sharpest and when it fogs. This clock is set by light, specifically by the rising and setting of the sun. Every morning, light enters your eyes and resets the clock. Every evening, darkness signals your brain to produce melatonin, the hormone that prepares you for sleep. The cycle is ancient. It predates humanity. It predates mammals. It is woven into the deepest layers of your biology. On the Moon, a single day lasts 29.5 Earth days, 14 days of unbroken sunlight, followed by 14 days of absolute darkness. Your circadian rhythm has no anchor. The sun does not rise in the morning. It sits on the horizon for 2 weeks straight. Then it disappears for 2 weeks. Your body does not know what to do with this. It cannot adapt because there is nothing to adapt to. The external cues that have regulated your sleep for every day of your life are gone. NASA lists circadian disruption as a critical risk factor for long-duration missions. Astronauts on the International Space Station experience 16 sunrises and sunsets every 24 hours as the station orbits Earth. Even that relatively minor disruption degrades sleep quality. Studies show ISS crew members average about 6 hours of sleep per night, well below the 7 to 8 hours recommended for optimal cognitive function. They report fragmented sleep, difficulty falling asleep, and reliance on sleep medication. On the Moon, the disruption is different, but potentially worse. Instead of too many light cycles, there are too few. 2 weeks of perpetual light, followed by 2 weeks of perpetual dark. Artificial lighting protocols can help, but they are a crude substitute for the natural rhythm of sunrise and sunset that your brain evolved to follow. The Mars 500 study, which confined 6 volunteers in a simulated spacecraft for 520 days to study the effects of long-duration isolation, documented severe circadian disruption. Heart rate rhythms lost their normal daily pattern. Cortisol, the stress hormone, became elevated. Physical activity declined. Neuromuscular performance degraded. Sleep quality collapsed. And this was in a controlled simulation on Earth, with normal gravity, stable temperature, and no radiation. Add the physiological stresses of the actual lunar environment, and the picture darkens considerably. But circadian disruption is only one dimension of the psychological assault. The other is isolation. On the International Space Station, astronauts can look out the cupola window and see the Earth filling half the sky. Every detail visible. The clouds, the oceans, the continents, the city lights at night. Home is right there, close enough to feel real. Communication delay to mission control is measured in fractions of a second. You can have a near-normal conversation with your family on the phone. Resupply ships arrive regularly. You are never truly cut off. On the Moon, Earth is a small disk in the sky, a marble held at arm's length, 384,000 kilometers away. It is beautiful. It is also profoundly, achingly far. The communication delay is 1.3 seconds each way. That does not sound like much until you try to have an emotional conversation through it. The lag strips the natural rhythm from dialogue. Comforting someone through a 2.5-second round-trip delay is an exercise in frustration, not connection. And if something goes wrong, if there is a medical emergency or an equipment failure or a psychological crisis, mission control cannot help you in real time. They can advise, they can talk you through procedures, but you are on your own for those critical first seconds that can mean the difference between life and death. NASA has studied the psychological health of astronauts extensively. The numbers are sobering. Research has found that over 22% of male astronauts and more than 85% of female astronauts reported anxiety symptoms during or after missions. More than 34% of males and over 43% of females reported symptoms of depression. And these numbers come from the International Space Station, which is comparatively comfortable. 6 people in a space the size of a large house, with regular resupply, video calls with family, fresh food deliveries, and the psychological comfort of knowing that in an emergency, you can be back on Earth in a few hours. A lunar habitat will be smaller, the crew will be smaller, the mission will be longer, the risks will be greater, and the exit options will be essentially zero. You cannot leave. If the person across the table from you in the tiny galley module begins to irritate you, if their habits grate, if their voice sets your teeth on edge, there is nowhere to go. No door to close, no walk around the block to clear your head. You are sealed inside a metal box with a handful of people you did not choose, breathing recycled air, eating the same food, staring at the same walls, performing the same tasks, on a world that is trying to kill you in 8 different ways at once. And outside the window, the landscape never changes. Grey dust, black sky, the same craters, the same rocks, the same horizons. Sensory monotony so complete that your brain begins to starve for novelty. Antarctic winter overstations are the closest analog we have on Earth. Small crews confined to isolated bases through months of polar darkness have consistently reported depression, insomnia, cognitive decline, and interpersonal conflict. Some stations have documented a phenomenon called the winter over syndrome, a combination of irritability, memory lapses, and social withdrawal that begins around the third month of darkness and deepens until the sun returns. And Antarctic crews have resupply options. They have evacuation protocols. They know that spring will eventually come. On the Moon, spring never comes. There is no seasonal change, no weather, no birdsong in the distance, no smell of rain, nothing alive outside the walls of your habitat except the dust and the rock and the vacuum. The Apollo astronauts famously described the overview effect, the profound sense of connection and perspective that comes from seeing the Earth from space. But they were visitors. They were there for days, filled with the adrenaline of exploration and the knowledge that they would soon go home. Artemis crews will not be visitors, they will be residents. And the overview effect, that initial rush of cosmic wonder, will eventually fade. What will replace it is the knowledge that you are standing on a world that wants you dead, kept alive by a thin wall of engineered metal and a team of people whose patience and competence cannot be guaranteed over months and years of confinement. No psychological framework exists for permanent habitation of a hostile world. We have never done it. We have lived in harsh environments on Earth, in deserts and tundras and underwater habitats. But we have never placed human beings in a situation where the environment is actively lethal from multiple directions simultaneously. The isolation is nearly total, the duration is open-ended, and the escape route requires days of preparation and a functioning rocket. The Moon attacks your mind through isolation, monotony, circadian destruction, and the slow creeping weight of knowing where you are. To survive it, humanity will need more than spacesuits and radiation shields. We will need somewhere to hide, somewhere the dust cannot reach, somewhere the radiation cannot penetrate, somewhere the temperature stays stable and the ground does not shake. And remarkably, the Moon itself may have provided exactly that. Deep underground, in tunnels carved by ancient volcanoes billions of years ago. Chapter 10: Going Underground. For over 50 years, scientists theorized that the Moon might contain caves. Not caves carved by water like on Earth, caves carved by lava. During the Moon's volcanic era, billions of years ago, rivers of molten basalt flowed across the surface, filling the vast low-lying basins that we see today as the Dark Maria. As the lava flowed, the surface cooled and solidified, while the molten rock underneath kept moving. Eventually, the lava drained away, leaving behind hollow tubes of solidified rock. On Earth, lava tubes are common in volcanic regions. Hawaii, Iceland, the Canary Islands all contain extensive networks of them, but Earth's lava tubes are modest, a few meters across, maybe 10 or 20 meters wide in exceptional cases. The Moon's reduced gravity changes everything. With only 1/6 of the gravitational force pulling down on the roof, lunar lava tubes can be enormous. Modeling suggests they could reach 300 meters or more in diameter. Cathedral-sized tunnels running for kilometers beneath the surface, with ceilings 40 or more meters thick. The theory was compelling, but for decades, that is all it was, a theory. Then the Lunar Reconnaissance Orbiter began imaging the surface in high resolution, and scientists started finding holes, pits, circular or elliptical openings in the surface that appeared to be skylights, places where the roof of an underground void had collapsed. Over 200 of these pits have been identified across the Moon, scattered across the Maria, each one a potential window into the world below. But a pit is not proof of a cave. A pit could be a shallow collapse with nothing behind it. To prove that a cave existed, you needed to see what was underneath. In 2024, that proof arrived. An international team led by researchers at the University of Trento in Italy published their findings in the journal Nature Astronomy. They had reanalyzed radar data collected by the mini-RF instrument aboard the Lunar Reconnaissance Orbiter, data that had been sitting in the archive since 2010. Using advanced signal processing techniques, they identified radar reflections from beneath the Mare Tranquillitatis pit, the famous pit located in the Sea of Tranquility near the Apollo 11 landing site. The reflections were consistent with an empty underground void, a cave at least 45 meters wide at the entrance, overhanging walls roughly 75 meters deep, and a passage extending 100 or more meters below the surface. For the first time in 50 years of theorizing, scientists had confirmed the existence of an accessible cave on the Moon. The implications were immediate and profound. A lunar lava tube solves multiple problems simultaneously. Radiation shielding, meters of solid basalt overhead, would block virtually all galactic cosmic rays and solar particle events. No material solution that humanity has ever designed can match the shielding effectiveness of 40 meters of rock. Temperature stability. Below the surface, insulated from the 300-degree thermal swings above, the temperature inside a lava tube is estimated to be stable at roughly minus 20 degrees Celsius, cold but manageable, and constant. No thermal cycling. No expansion and contraction fatigue destroying your equipment. Micrometeorite protection. Nothing gets through 40 meters of rock. Dust mitigation. Inside a sealed cave, the electrostatically charged razor dust of the surface cannot reach you. A lava tube is not just shelter. It is the closest thing to a habitable environment that the Moon offers. And the Moon built it for free, billions of years ago, without knowing that one day a species from the blue planet next door would desperately need it. The discovery accelerated research. In 2025, a team demonstrated that gravity sensors could reliably detect lava tubes down to 26 meters below the lunar surface. This means future missions could survey potential sites from orbit or from rovers before committing to a location. In the same year, China's Chang'e 4 rover, operating on the far side of the Moon, detected a roughly 3-meter void just beneath the surface using ground-penetrating radar. It was the first subsurface cavity found by an active surface mission. Smaller than the Mare Tranquillitatis cave, but proof that voids exist across the Moon, not just in one location. And in February of 2026, a European team tested a cooperative robotic exploration system in the lava caves of Lanzarote in Spain's Canary Islands. 3 robots worked together. One mapped the cave entrance from above. Another deployed sensors along the rim. A third was lowered by cable into the darkness below, creating 3-dimensional maps of the interior autonomously. The technology is being developed specifically for lunar cave exploration. The idea is to send robots first, map the cave, assess its structural integrity, identify hazards, determine whether the ceiling is stable, whether the floor is navigable, whether the dimensions are sufficient for habitation. And only then, once the underground environment has been thoroughly surveyed, would you send humans. The realistic pathway to a lunar settlement begins to come into focus. The first habitats will be on the surface, near the South Pole, close to permanently shadowed craters for water access, and on sunlit ridges for solar power. These surface habitats will be vulnerable to every threat we have discussed: dust, radiation, temperature, quakes, micrometeorites. They will be temporary, functional but fragile. The long-term plan shifts underground. Lava tubes as radiation shelters first, during solar particle events. Then as storage facilities, protecting supplies and equipment from the thermal environment. Then as pressurized habitats, with inflatable structures deployed inside the cave and gradually expanded. Pressurization studies suggest it may be feasible to seal and pressurize small sections of a lava tube with breathable air using inflatable membrane systems. The rock walls provide structural containment. The pressure keeps the membrane rigid. Inside, you could have a shirt-sleeve environment, a space where astronauts could remove their helmets, stretch their legs, and live in something that feels less like a spacecraft and more like a home. But access is a problem. The pit entrances that have been identified from orbit have steep vertical walls. Some may be unstable. Getting equipment and people down into a cave through a 75-meter drop in 1/6 gravity is not trivial. Robotic preparation would need to come first. Anchors, winches, structural reinforcement of the entrance. Communication relays, because radio signals do not penetrate rock. Lighting, because the interior of a lunar cave is the most absolute darkness imaginable. No light has ever entered these spaces. Not a single photon since the roof solidified billions of years ago. The first generation of lunar settlers will live on the surface and work on the surface and endure the surface. But the second generation, if there is a second generation, may live underground, in tunnels carved by ancient fire, sealed by human ingenuity, protected by the same rock that has shielded the moon's interior from the cosmos for 4.5 billion years. Lava tubes offer shelter, but only if we can find them, reach them, and confirm they will not collapse. And even underground, the moon has one more challenge waiting. Everything you bring with you starts to fail. The dust follows you in. The equipment degrades. The supply chain from Earth stretches thin. And the question shifts from whether you can survive the moon to whether you can build on it. Chapter 11. Building on a world that hates you. Here is the paradox at the heart of lunar construction. The very dust that threatens to kill you is also your primary building material. You cannot haul enough concrete, steel, and shielding material from Earth to build a permanent base. The launch costs alone would bankrupt a nation. At roughly $1 million per kilogram delivered to the lunar surface, a single habitat module made of Earth materials would cost more than some countries spend on their entire space programs. The only economically viable path to permanent infrastructure is to build with what the moon provides. And what the moon provides is regolith, the same toxic, electrically charged, razor-edged powder that clogs your equipment and shreds your lungs. The concept is called in situ resource utilization, ISRU. It is the foundational technology for any permanent presence beyond Earth. The idea is elegant. Take the lunar soil, heat it in a focused beam of sunlight or a microwave until the particles sinter together, fusing into a solid mass. Or feed it into a three-dimensional printer that deposits layers of processed regolith, building structures from the ground up, one pass at a time. Radiation shields, landing pads, roads, habitat walls, all made from the moon itself. China's Chang'e 8 mission, planned for 2028, will be the first to attempt this on the lunar surface. The lander will carry experiments designed to manufacture building materials from lunar soil using three-dimensional printing technology. If it works, it will be a proof of concept for everything that follows. If it does not, the timeline for permanent habitation stretches further into the future. But processing regolith creates its own problems. Digging, moving, heating, and depositing lunar soil kicks it into the air, and in 1/6 gravity, it stays there. Every construction activity on the lunar surface would generate clouds of the same submicron particles that caused Harrison Schmidt's lunar hay fever, except on a far larger scale and over far longer durations. The workers building the base would be exposed to the very toxin the base is designed to protect them from. Additionally, processing generates static charge. The particles cling to every surface, every mechanism, every seal, every optical sensor. The dust is not just a hazard. It is an adversary, that actively fights your attempts to use it. Power is the next challenge. Solar panels work beautifully on the sunlit ridges near the poles. Near constant illumination means near constant power generation. But any activity inside the permanently shadowed craters, where the water ice is, where the most valuable resource on the moon sits waiting in the dark, requires independent power. Solar panels do not work in permanent shadow. You need another source. NASA is pursuing fission surface power, a compact nuclear reactor on the moon capable of generating roughly 40 kilowatts, enough to power a small outpost. The target is to have a prototype operational by the early 2030s. But nuclear reactors generate heat, require cooling systems, and must be maintained. And placing a nuclear reactor on or near an active fault zone introduces seismic risk that engineers are only beginning to evaluate. As Nicholas Schmer observed, he would not want to put a nuclear reactor on an active fault. The American Society of Civil Engineers has begun drafting guidelines for lunar structures that borrow from earthquake engineering, base isolation techniques, flexible foundations, structural damping, all designed to protect buildings from sustained ground shaking. But these techniques were developed for earthquakes that last seconds, not moonquakes that last hours. And then there is the supply chain. On Earth, if a critical component fails, you order a replacement. It arrives the next day. On the Moon, the nearest warehouse is 384,000 kilometers away. Transit time from Earth to the lunar surface is a minimum of 3 days, assuming a rocket is ready to launch, a payload is packed and tested, and everything goes according to plan. In reality, the gap between identifying a critical need and receiving the replacement part would be measured in weeks or months. This means that everything on a lunar base must be designed for redundancy and self-repair. Critical systems need backups. Backup systems need their own backups. Spare parts must be pre-positioned in sufficient quantities to cover anticipated failures, plus a margin for the unanticipated ones. Every kilogram of spare parts is a kilogram of something else that could not be brought. Food, water, scientific instruments, medical supplies. The mass budget of a lunar base is a zero-sum game where every decision has consequences. Autonomous maintenance will be essential. Robots that can inspect, diagnose, and repair equipment without human intervention, but the same environment that demands robust automation actively degrades it. Dust coats, sensor lenses. Abrasive particles wear down moving parts. Thermal cycling fatigues, electrical connections. The machines designed to fix things will themselves need fixing by other machines that will also need fixing, in an environment that is systematically destroying everything it touches. The Apollo astronauts found all of this in 3 days. The dust, the abrasion, the equipment degradation, the difficulty of working in bulky suits in a hostile environment. They managed because the missions were short, the objectives were limited, and they could afford to push through problems knowing they would be home in days. A permanent base cannot operate that way. A permanent base must endure, year after year, thermal cycle after thermal cycle, moonquake after moonquake. With no cavalry coming over the horizon if things go wrong, the engineering challenges are immense. They are solvable, probably, given enough time and money and ingenuity. But they raise a deeper question that no amount of engineering can answer. A question about law, about politics, about the fundamental rules that govern who gets to do what on a world that belongs to no one. Who owns the moon? Who decides who can mine its resources? Who gets the water? And what happens when two superpowers arrive at the same crater and disagree? Chapter 12. Who owns the moon? In 1967, at the height of the Cold War, while the United States and the Soviet Union were locked in a race to be the first to land a human on the lunar surface, the two superpowers agreed on something remarkable. They agreed that nobody could own the moon. The Outer Space Treaty, signed in 1967 and eventually ratified by over 100 nations, declared that outer space, including the moon and other celestial bodies, is the province of all mankind. No nation may claim sovereignty over any part of the moon. No country can plant a flag and declare that the ground beneath it belongs to them. The moon, the treaty said, shall be used exclusively for peaceful purposes. It was a product of its time, a grand idealistic framework designed to prevent the extension of Cold War territorial disputes into orbit. And for decades, it worked, largely because nobody was doing anything on the moon that required a more specific set of rules. That era is ending. The Outer Space Treaty was written before anyone imagined mining lunar water ice for rocket fuel, before anyone seriously proposed extracting helium-3 from the regolith for fusion energy, before any nation planned to build permanent infrastructure on the lunar surface. The treaty prohibits territorial claims, but says nothing about resource extraction by private companies. It prohibits weapons of mass destruction in space, but does not address the question of who gets to drill for water in a specific crater. It is a document that answered 1967's questions and is now struggling with 2026's reality. The United States has attempted to fill the gap with the Artemis Accords, a set of bilateral agreements between the United States and partner nations that establish norms for lunar exploration. Signed by over 50 nations as of 2026, the accords include provisions for transparency, interoperability, and the creation of safety zones around operational sites. They affirm the right to extract and use space resources, a principle that the United States had already enshrined in its own domestic law with the Commercial Space Launch Competitiveness Act of 2015. Under American law, a company that extracts water from a lunar crater owns that water. The Artemis Accords extend this principle to partner nations. China and Russia are not signatories to the Artemis Accords. They have their own framework. The International Lunar Research Station, the Joint China-Russia Initiative, operates under a separate set of agreements with its own partner nations. China has invited over 50 countries to participate. The two frameworks coexist, but do not align. There is no mechanism for resolving disputes between them, no international body with the authority to adjudicate competing claims, no lunar police force, no court of appeals, and the potential for conflict is not abstract. Both Artemis and the International Lunar Research Station are targeting the same destination, the lunar South Pole. Both want the water ice. Both need the permanently sunlit ridges for solar power. And here is the geographical reality that makes this dangerous. The South Pole is not a vast open plain with room for everyone. The optimal sites, the locations that combine nearby permanently shadowed craters for ice access with sunlit ridges for power, are geographically constrained. There are a limited number of good spots. And when two missions from competing frameworks arrive at the same good spot, the Outer Space Treaty offers no guidance on who goes first, who stays, or who moves. The treaty says no nation can claim the land. But does extracting water from a crater constitute a claim? If you build a road to a crater and install drilling equipment and begin producing water and oxygen, have you effectively claimed that site even if you have not planted a flag? If another nation sets up operations nearby and their activities interfere with yours, their dust clouds contaminating your solar panels, their seismic surveys destabilizing your crater walls, who arbitrates? The answer right now is nobody. The legal framework is thinner than the atmosphere the moon does not have. And then there is helium-3. The sun has been depositing particles on the lunar surface for billions of years. Among them is helium-3, an isotope that is rare on Earth but relatively abundant in the top layer of lunar regolith. Helium-3 is a theoretical fuel for aneutronic fusion, a type of nuclear fusion that produces energy without generating dangerous radioactive waste. If humanity ever develops a working helium-3 fusion reactor, the moon's regolith could become the most valuable energy resource in the solar system. China's International Lunar Research Station roadmap explicitly includes helium-3 extraction as a long-term objective. Estimates suggest the Moon's regolith contains millions of tons of it, but the concentrations are extremely low, measured in parts per billion. Extracting usable quantities would require processing truly enormous volumes of soil, essentially strip mining the lunar surface on a scale that would make terrestrial mining operations look modest by comparison. The environmental implications are significant, even on a world without an environment in the traditional sense. Processing millions of tons of regolith would generate vast quantities of airborne dust, alter the surface topology, and potentially contaminate nearby sites. The question is not whether helium-3 is there. It is whether the geopolitical race to claim it will outpace the technology to use it. Fusion reactors capable of burning helium-3 do not yet exist. They may not exist for decades. But the competition to establish presence and precedent at the sites where helium-3 is most accessible is happening now. The legal framework is fragile. The resources are finite. The competition is real. And through all of it, the Moon waits. Indifferent to treaties and borders and ambitions, it does not care who comes. It will treat them all the same. The dust will coat their equipment. The radiation will shred their DNA. The quakes will shake their habitats. The cold will test their machines. The Moon does not play favorites. It is an equal opportunity destroyer. And perhaps that is the most important thing the Moon can teach us. That in the face of an environment this hostile, this unforgiving, this indifferent to human rivalry, cooperation is not just a moral ideal, it is a survival strategy. The question is whether we are wise enough to learn that lesson before the competition for lunar resources teaches it to us the hard way. Chapter 13. The First Year. Let us walk through it, not as science fiction, not as speculation, as a thought experiment grounded in everything we know. Imagine the first crew to establish a sustained presence on the lunar surface. They are not Apollo astronauts on a 3-day visit. They are residents. Their mission duration is 1 year. Here is what that year looks like. Day 1. The lander touches down on a sunlit ridge near the South Pole. The engine cuts out. Silence. The crew sits for a moment, letting the reality settle. They are on the Moon. The first humans to stand here in over 50 years. The first ever to stand here with the intention of staying. The hatch opens. The first boot presses into the regolith. The footprint is perfect. Every ridge of the sole captured in powder that has not been disturbed in 1 billion years. Within minutes, the dust begins its work. It coats the lower legs of the suits. It works into the joints. It scratches the visor coatings. The astronauts set up the initial equipment, solar panels, communication antennas, a small seismometer. They inflate the habitat module and begin the transfer of supplies from the lander. Every airlock cycle brings dust into the habitat. The air filtration system engages. The filters begin to load. The smell of burnt gunpowder hangs faint in the recycled air. The first lunar sunset approaches. After 14 days of continuous sunlight, the sun drops below the horizon. The temperature outside begins to fall. Within hours, it is minus 100 degrees. Within a day, it is minus 150. The habitat's thermal control system works over time. The nuclear power unit, positioned carefully away from the nearest identified fault, hums steadily. Inside, the lighting switches to an artificial day-night cycle designed to preserve circadian rhythm. The crew knows it is dark outside. They can see it through the porthole. Blackness. Absolute, featureless blackness, broken only by the stars and the small blue disk of Earth, 384,000 kilometers away. The first long night begins. By month 2, the circadian disruption is measurable. Sleep logs show fragmented rest. 2 crew members report difficulty falling asleep. 1 reports unusually vivid dreams. Mood assessments, filled out on digital tablets and transmitted to mission control, show subtle shifts. Increased irritability, decreased patience. Nothing alarming. Nothing that would trigger a formal intervention. But the trend is there, visible in the data if you know where to look. By month 3, the first bone density scans are performed. The results confirm what the models predicted. Measurable loss, primarily in the hips and lower spine. Exercise protocols are intensified. The crew now spends 2.5 hours per day on the treadmill and resistance machines. It is tedious, it is exhausting. It competes with scientific work and maintenance tasks. One crew member begins to resent it. The resentment is small. It is noted in a private journal entry. It is not shared with the group. During the 4th month, the first equipment failure occurs. A seal on the secondary airlock degrades from thermal cycling. The atmospheric monitoring system detects a slow pressure drop. The crew identifies the source, replaces the seal from pre-positioned spares, and restores integrity. The incident takes 6 hours. For those 6 hours, the crew operates on backup atmospheric protocols, wearing their emergency oxygen masks while they work. Nobody panics. Everyone follows procedure. But that night, sleep is worse than usual for everyone. By month 6, the cumulative radiation dose is approaching the limits established for shorter missions. The crew has been diligent about limiting unnecessary exposure during extravehicular activities, staying inside during the peak hours of known solar activity, and sheltering behind the thickest parts of the habitat during solar particle events. But galactic cosmic rays do not have peak hours. They are constant. They pass through the walls 24 hours a day. The dosimeters track the accumulation steadily. One crew member develops a persistent cough. The medical officer examines them. The cause is unclear, possibly dust exposure from the airlock cycles. Possibly an irritation response to the recirculated air. Possibly nothing. There is no X-ray machine. There is no clinic. The treatment options are limited to the medical supplies on board. The cough is monitored. It does not worsen, but it does not go away either. Month 8. A shallow moonquake registers on the seismometer. Magnitude 2.8. On Earth, you would not notice a 2.8. On the Moon, the shaking lasts 45 minutes. The habitat sways perceptibly. Equipment rattles on shelves. A container of tools falls to the floor. The structural monitoring system shows no damage. Everything held. But for 45 minutes, the crew sat inside a metal box on the surface of a world that was visibly, tangibly, undeniably moving beneath them. The psychological impact is deeper than the physical one. The ground was supposed to be the one thing that stayed still. Month 10. Dust accumulation on the external solar panels has reduced power output by roughly 15%. An extravehicular activity is scheduled to manually clean them. 2 crew members go outside, brushes in hand, and spend 4 hours wiping abrasive powder off photovoltaic cells. Each brush stroke launches particles into the vacuum, where they drift and settle and must be brushed again. The EVA exposes both crew members to additional radiation and additional dust inhalation during the airlock cycle. The panels are cleaned. Power output recovers. The process will need to be repeated in another few months. Month 12, the 1-year mark. The habitat has survived. Every system shows degradation, but everything still functions. The air is breathable. The water is drinkable. The power is sufficient. The structure has held through thermal cycles, micrometeorite impacts, and at least one moonquake. The crew is alive. They are functional. They have performed their scientific tasks, maintained their equipment, and kept each other alive for 365 days on the most hostile surface in the inner solar system. But they are not the same people who arrived. Their bones are thinner. Their muscles are weaker. Their eyes have changed. Their immune markers are abnormal. Their sleep is fragmented. Their patience is frayed. Every system in the habitat shows wear. Seals that were fresh a year ago are now suspects. Filters that were clean are now loaded. Spare parts that were abundant are now running low. The next resupply mission is 2 months away. The question is no longer, can we get there? We have answered that question. The question is no longer, can we survive for a year? We have answered that too, at least in this thought experiment. The real question, the one that will define the next chapter of human exploration, is this: can we stay? Not for a year, for a decade, for a generation. Can we build something on the moon that outlasts a single mission? Something that grows? Something that endures? And the answer to that question depends not on the moon. It depends on us. Chapter 14. Why we go anyway. Every chapter of this documentary has been a warning. The dust is toxic. The radiation is unstoppable. The ground is cracking. The temperature destroys equipment. The isolation erodes the mind. The body breaks down from the inside. The supply chain is impossibly thin. The legal framework is a relic from a different era. The moon is not a stepping stone. It is a gauntlet. And some scientists argue, not unreasonably, that we should not send people there at all. The case for robots is strong. Robots do not need air. They do not lose bone density. They do not get depressed. They do not develop mysterious coughs from dust exposure. They do not argue with each other in confined spaces. They do not need 2 hours of exercise per day. They do not require food or water or medical supplies. Every problem described in this documentary either disappears or shrinks dramatically if you remove the human element. A robotic outpost at the South Pole could drill for water ice, process regolith, test building techniques, and monitor seismic activity for years without risking a single life. The science could be done remotely. The resources could be extracted by machines. The reconnaissance of lava tubes could be performed by robots lowered on cables into the darkness. And yet, we have never been a species that sends only machines. We have always sent ourselves. Into the unknown, into danger, into places that offered no guarantee of return. We crossed the oceans in wooden ships, knowing that storms could swallow us whole. We climbed mountains knowing that the cold could kill us before we reached the summit. We went to the moon in 1969 in a spacecraft with less computing power than a modern calculator, balanced on top of a controlled explosion, guided by mathematics and courage, and the absolute refusal to accept that something was impossible simply because it had never been done. We did not go back for 50 years, not because the moon became harder. Because we convinced ourselves the job was finished, we planted the flags, we collected the rocks, we won the race. And then we turned away and let the memory of what we had achieved slowly fade into history. Something our grandparents did, something that belonged to another era. But the moon did not go anywhere. It waited, patient, indifferent, exactly as hostile as it had always been. And now, half a century later, we are turning back to face it again. Not as visitors this time, as settlers. And the stakes are incomparably higher, because the moon is the test. If we cannot learn to live on a hostile world 3 days from Earth, with resupply possible and communication near instant, we will never reach Mars. Mars is 7 months away. The communication delay is 20 minutes each way. There is no resupply. There is no evacuation. There is no abort to Earth orbit if something goes catastrophically wrong. Mars is the moon's dangers multiplied by distance and duration and the absolute finality of being truly, completely alone. Everything we learn on the moon, every solution we develop for dust mitigation, radiation shielding, psychological endurance, autonomous maintenance, resource extraction, medical care in isolation, everything feeds directly into the architecture that will one day carry humans to Mars and beyond. And the moon offers something that no other destination can provide: fuel. If water ice at the South Pole can be extracted in usable quantities, the moon becomes a refueling station for the inner solar system. Spacecraft do not have to carry all their propellant from Earth's deep gravity well. They launch to lunar orbit, refuel with hydrogen and oxygen produced from lunar ice, and proceed outward, to Mars, to the asteroids, to the moons of Jupiter and Saturn. The economics of space exploration change fundamentally if the moon can be made to produce rocket fuel. Every mission becomes cheaper. Every destination becomes closer. The moon is not the end point. It is the door. And then there is the science that can only be done on the moon. A radio telescope on the far side, permanently shielded from the electromagnetic noise of Earth. A telescope that could detect signals from the earliest moments of the universe, frequencies that are drowned out by the cacophony of human civilization on every Earth-based instrument. Geological samples from permanently shadowed craters, volatiles preserved in the cold for billions of years, records of the early solar system that exist nowhere else. A laboratory for studying the human body in partial gravity, something we have never measured. We know what microgravity does. We know what full gravity does. We have never observed what 1/6 gravity does over months and years. The medical data from a sustained lunar presence would reshape our understanding of human physiology. We went to the moon 6 times. Each time, we stayed less than 3 days. We were visitors passing through too quickly for any of the dangers to fully reveal themselves. We learned what we could in the brief windows we allowed ourselves, and then we left. Going back is one thing. Staying is something else entirely. Staying means accepting the dust, enduring the radiation, riding out the moonquakes, watching your bones thin and your muscles shrink and your circadian rhythm dissolve, knowing that these are the costs of being somewhere extraordinary, somewhere that no living thing has ever called home. The moon does not care about our treaties, or our rockets, or our timelines, or our ambitions. It does not care who gets there first, or who plants the most flags, or who extracts the most water. It is what it has always been: quiet, patient, beautiful from a distance, lethal up close. A wound in the sky left over from the most violent event in Earth's history, slowly cooling, slowly cracking, slowly dying under the full assault of the cosmos. It will outlast us. It will outlast our civilization. It will outlast every flag and footprint and habitat we leave on its surface. In 1,000,000 years, the dust will have buried everything. In 100 million years, the regolith will have ground it all to powder. In 1,000,000,000 years, the sun will be a little brighter, the earth a little warmer, and the moon will look exactly as it does tonight. Grey and white and ancient, hanging in the sky, keeping its secrets. But we are what we have always been too, a species that looks at the thing that might kill us and walks toward it anyway. Not out of recklessness, not out of ignorance, out of something deeper, something woven into the same DNA that the cosmic rays are trying to destroy. Curiosity, restlessness, the absolute refusal to accept that the horizon is the end of the world. We know the moon is trying to kill us. We know the dust is toxic. We know the radiation is relentless. We know the ground shakes and the cold bites and the isolation haunts. We know all of it now, and we are going anyway. Because we have to know what is on the other side. We have always had to know. And the moon, for all its hostility, for all its patience, for all its indifference to human life, is the next step on a journey that started when the first hominid looked up at the night sky and wondered what those lights were. We are still that creature, still wondering, still reaching, still walking toward the thing that might destroy us. Because the alternative, staying home, staying safe, staying comfortable, staying small, is something we have never been able to do. The moon is waiting. It has been waiting for 4.5 billion years. It can wait a little longer, but we cannot. And so we go. If you enjoyed this deep journey through science and the challenges of space, please like this video and subscribe to the channel. Your support makes these detailed stories possible, Tell us in the comments, would you go to the moon? Knowing everything you have just heard, knowing every danger, every risk, every way it can hurt you, would you still go? And if not the moon, where? Where would you go if you could go anywhere in the universe? These are not just questions for astronauts, they are questions for all of us. Because the next chapter of human exploration is not being written by a single agency or a single country. It is being written by a species, our species. And every question we ask brings us one step closer to the answer. Thank you for listening. We will see you in the next journey.